Okay, guys, so getting into chapter 5, we're eventually working our way to a really important topic, normal model, but not there just yet. First, we have to understand some really key things before getting to anything with the normal distribution. So the first thing that we'll talk about are z-scores, okay? So here's those test scores from Mr. Pryor's class. We saw those in class when we were doing cumulative relative frequency graphs, okay? So Jenny was the one who's, it is bold here, but it's hard to tell. Jenny's the one that scored that 86, okay? So what if I ask you, where does Jenny's score of 86 fall relative to the mean of this data? Well, because the mean score was 80, we can see that Jenny's score is above average, okay? So if the mean was 80, then her score of 86 is definitely above average. But I guess now we can ask ourselves, well, how much above average, okay? So we can describe Jenny's location in the distribution of her class's test scores by telling how many standard deviations above or below the mean her score would be. So remember that we'd said that standard deviation is how much it varies, but you can think of it as a distance as well. So if you wanted to kind of think of her score in terms of a distance away from the mean, you are referring to its standard deviation. So because the mean was 80, and her score was 86, and the standard deviation for the set of data was about 6, then we would say that this puts her about 1 standard deviation away from the mean. Okay, so converting observations like this from like an original value, like her 86 test score, and we translated it to a standard deviation, this is known as standardizing, okay? It is the idea of a z-score. So a z-score tells us how many standard deviations from the mean an observation falls. It also will tell you what direction. So if x is an observation from a distribution that has a known mean and standard deviation, the standardized value of x is, we call them z-scores. It's your observation minus your mean divided by your standard deviation. Okay, so a z-score tells us how many standard deviations away from the mean that your observation falls. It will also tell you kind of what direction. So if your observation is larger than your mean, your z-score is going to be positive. As opposed to your observation being smaller than your mean, you'll have a z-score that's negative. Okay, so here's Jenny. She earned an 86. Her class mean was 80. The standard deviation was, I said, about 6. It was more like 6.07. So if I had to calculate her standardized score or her z-score, I would do as follows. Now I understand that 0.99, which is about 1, which is what we said before, that Jenny is about 1 standard deviation or 0.99 standard deviations away from her mean. Okay, we can more than likely, or I shouldn't say more than likely, but what z-scores are super useful for is to compare. Okay, so individuals within different distributions. So for an example of this would be so Jenny earned a score of 86 on her stats test. Mean was 80, standard deviation 6.07. Now I'm going to tell you that she earned an 82 on her chemistry test. So the chemistry scores had a fairly symmetric distribution with a mean of 76 and a standard deviation of 4. So now I can say, although they were very, very different tests, they were very, very different classes, so the distribution would look very, very differently. But I can use a z-score to be able to compare whether I believe she did better on her chemistry test or her statistics test, regardless of the score. You can't compare the scores of how they are now. So you'd have to standardize them using your z-scores in order to understand a comparison between the two. So we already did the z-score for her stats class as a chemistry class, in her chemistry class, her standardized score would have been 1.5, which means technically in chemistry, she was 1.5 past the mean. Okay, that means that she technically did better on her chemistry test because she was 1.5 above the mean as opposed to 0.99 above the mean in her stats class. Okay, so we often will standardize observations to express them on kind of like a common scale. So you can't normally compare. Stats to chemistry tests. They're very different. Even the distributions would be different, okay? But it's kind of like giving it a common scale so that you are able to make some comparison between the two. So I could tell you to compare the heights of two completely different children, different genders at different ages. So let's say there's, okay. So if I wanted to compare heights of two children of different ages, right, and even different genders. So let's say there's Jordan, okay? Okay, Jordan's 2 years old, okay? Female, okay? Her height right now, 89 centimeters tall, okay? Let's talk about Zach. Zach is 3 years old, okay, a male, and let's say that he's 101 centimeters tall, okay? Well, as it stands right now, you can't really compare and say who was taller because it's just a completely different situation. One's a male, one's a female, that tends to be different, and one is 2 years old and one is 3 years old, okay? But if I compared a z-score, then I would be able to do it. So if I told you that there was a z-score, and I'm just making this up, if I told you the Jordan z-score for 89 centimeters tall was about 0.5 standard deviations, okay? And I told you that Zach's was, let's say 1, okay? Standard deviation above the mean. Now we have a better understanding. Now we know that Jordan is only half a standard deviation above the mean, where Zach is 1 full standard deviation above his mean. And so we would say that Zach is definitely taller relative to the boys his age than Jordan is relative to the girls her age. So it allows us to compare within two things that normally would not be able to be compared. And that's it for z-scores. We'll keep working on these things, though.